Well, thank you very much, Stephanie. We are all at nTopology are very excited to be presenting today through Additive Manufacturing Media and show what our company has been doing and what our unique solutions are for the additive manufacturing space. Now, I'll give you a little bit of background on our company, our software offerings, our vision, and that'll pave the way for Alex and Blake just after me to get into the specifics of implicit modeling in nTopology platform and how it's furthering and enabling additive manufacturing. Now, first, a little background on our company and who we are. nTopology is a rapidly growing software company making design engineering solutions for advanced manufacturing. And when we say advanced manufacturing, that includes additive manufacturing, amongst other things. Now, we started in 2015 based in New York City, and we have this goal of creating a better product development system that's driven by data and physics. And those are two important words there, data and physics, and we'll talk more about those. Now, our vision has to do with helping engineers better define, represent, and lock down various engineering processes digitally. Now, all of those things are important, no matter what sort of product you're talking about. But I would argue that in light of the rise of additive manufacturing, and there's so many new ways to make a product and define it, understanding the engineering process is paramount, especially with additive manufacturing. So we accomplish this defining, representing, and locking down parameters. We do these things by combining elements of design, engineering, simulation, and advanced manufacturing in this digital process that makes engineering knowledge reconfigurable and reusable by other engineers in an organization. So the easiest way to summarize all that and put it succinctly, I would say, is it's smarter and more efficient use of data. So there's that word data again. So that's a very, very high level, the 10,000-foot view of who we are and what our mission and vision is and what we've set out to do. So regarding some of the products that nTopology has, nTopology is probably best known for creating nTopology element. So if you've ever seen a demonstration, screenshots, or a video of our software, it's probably been from Element. Now, it's a wonderful point solution, and it's been out for a few years, and it enables engineers to easily create these optimized lattice structures for additive manufacturing. It's very impressive. From there, we took all that learned knowledge we had from Element to create this next generation tool called nTopology Platform, or as we shorten it, nTop Platform. Now, Platform, as Blake's going to show you in a few moments, has a greatly expanded scope as compared to Element. It's generally going to do all the things that Element does, but as I mentioned a few slides ago, and in talking about our mission and vision, nTopology has this larger vision for an engineering environment integrating design, simulation, and advanced manufacturing processes. That's what Platform is all about. And it's really best to describe in terms of its benefits, and I could succinctly put those in three ways. High performance geometry, and this is regardless of the complexity of a model or a design you have, from the simplest to the most complex. So you'll see when Blake does this demonstration that because of this implicit modeling technology, model generation is fast, it's robust, and it doesn't fail. It's really impressive. The second is connected engineering systems. So this is the only design solution that allows an engineer to simultaneously consider the function, geometry, simulation results, and manufacturing, all within this computational process. And the third would be capturing engineering workflows. So by using engineering notebooks and computational design technology, it's going to deliver a highly specific control over advanced mechanical designs. So the point of that is it helps teams document and reuse shared knowledge and proven workflows in an automated way. And some of these things, again, you're going to see as Blake shows off the software. Now, quite honestly, each of these topics that I just mentioned, those 3 bullet points, they really have several subtopics, and we could be showing future information sessions just like this one in the future, and I think we will be doing that. But again, going back to something I said earlier about data, this is really the common thread that I would argue that you see with those benefits and those 3 points. Take a step back. Today, think about data. It's everything. It's everywhere. You first have to capture it, understand it, use it properly, configure it, optimize it, and the list goes on and on of all the things that you need to do with data to adequately make a part and have it be successful, make a product. Now, in nTopology's products, we're providing an environment where through this implicit modeling technology and nTop platform, data can be integrated, locked down, and quickly processed to further enable additive manufacturing. Now, the reality is that because of where additive manufacturing is today, our modern manufacturing techniques have generally outpaced our design solutions. What you'll see today in the context of additive manufacturing is that nTop platform really speaks to that first bullet point of high performance geometry, the creation of something that's either simple or complex. nTop lets you define, create, test, capture, lock down your design ideas, and create manufacture-ready outputs. So I would argue that with this implicit modeling technology and nTop platform, the gap between design and manufacturing capabilities is really starting to shrink. Now, Alex is going to come on in a second, and he's going to give you some background on implicit modeling and that technology in the context of additive manufacturing and further set the stage for Blake's demonstration. Alex, why don't you go ahead and take it away?
Thanks, John. Hey, this is Alex. Today I'm going to go over some of our core technology that enables design for additive in nTop platform. The main enabler is our implicit geometry kernel that John has been talking about. To understand implicit geometry and its key benefits, it's important to review the different ways geometry is represented. On the left here, we have a mesh representation. Meshes are defined by points in a coordinate system and their subsequent triangles. STLs are a common mesh file type, and anyone in the additive industry knows that they are really very hard to work with. The files get extremely large easily, they're inaccurate, and contain no real engineering data. In the middle, we have a BREP surface representation, which is a continuous representation where the geometry is represented by the surfaces, edges, and vertices that bind it. They are much easier to work with than mesh files, but there are still limitations. As the model gets more complex and design changes happen, features start breaking and rebuild errors are common when there are inconsistencies in the binding of these surfaces, edges, and vertices. On the right, we have an implicit representation. So this is a mathematical representation where the geometry's volume is simply represented as a math function. This allows us to reparameterize a specific geometry simply by tweaking that function's coefficients or nesting it in another function, and we'll go more into that later in the demo. Without the need to create explicit representative geometries such as faces or triangles, the speed of our implicit-based software is significantly faster, and the files are much more lightweight and easier to work with. For example, on that right here, that file is around 4 kilobytes. One of the key application areas of this technology is for design exploration and design of experiments, which complements the speed and iterative nature of additive manufacturing extremely well. In this picture, we have an example of a design study with 200,000 parameter changes. And during that, there were 0 rebuild errors, which really is impossible in traditional design systems. Here, we're really kind of hitting the point that nTop platform for additive is a robust representation resulting in increased design iterations. So as far as these characteristics, it's a multi-dimensional design exploration. So it's one integrated environment where design, simulation, and manufacturing can have input in the product definition. So implicit modeling de-risks design changes. Because there are no rebuild errors, engineers are encouraged to explore the design space more fully. And all of this kind of goes towards enabling rapid and iterative product development. So engineers can be more efficient and spend time on engineering work that matters. And now I'm going to hand this over to Blake for a demo of the nTop platform.
Thanks, Alex. So this is Blake. I'm an application engineer here at nTopology, and I'm excited to take you through this demonstration of how we use nTop platform, specifically with respect to design for additive manufacturing. And not only does nTop platform allow us to drive really interesting, intricate, and complex geometries, it also enables this new workflow that allows us to really rapidly and efficiently explore a design space. So I'm going to do that in the context of this F1 brake pedal that you may have seen before if you're a previous nTopology element user, or perhaps you've read some of the blog posts that are on the website. So normally I would actually model this geometry here that you see on the screen directly in Platform as an implicit. However, I did want to showcase Platform's ability to import parasolid boundary representations from existing CAD software. So even if you have a part that was designed elsewhere, you can bring it in and we can do work on it. So you'll see that I have kind of two regions that I've brought in. One is this solid keep area of the pedal that I want to keep solid. And then the other is this lattice area. So this lattice area is an interior region where I want to explore how I might fill this with a type of lattice, explore different lattice types, and control the geometry of said lattice. So I'm able to parameterize that lattice space and set these UVW divisions here. So you can see that I've set it to 32, 3, 4. What that means is that along this direction, I have 32 unit cells. Going in the Z direction, I have 4. And then in the thickness, you'll see that this is about 3 units across. So that's what that means when you look at that variable UVW divisions. And we can always change this. It will rebuild super rapidly, bring that all the way up to 100. Just for fun, we're going to kind of see what happens when we bring that up to 1,000. So now you see this sort of wall of lattice. But if we zoom in really closely, you'll see that all the geometry is there. So this is probably fairly impractical for what we're trying to do. So I'm going to bring this back down to a more reasonable number, back to 32. Not only can we change these UVW divisions, we can also explore the type of unit cell that we might want to have. So here's this diamond unit cell. There's lots of others that you can see that come with Platform, plus the future ability to define your own unit cell. I'm going to go with this body-centered cubic lattice type here. So you can see now we have this lattice. This is a beam-based representation of this lattice. It has 0 thickness right now. What I want to do is I want to kind of give it some thickness and union it with this keep area. So first things first, I want to give the beam a thickness of, for now, 1 millimeter. And in this final part here, I have it defined as 1 millimeter beams union to that outside keep area. So let that regenerate. Now we have our part. One of the main issues that we see oftentimes with additive manufacturing and using lattice structures is this interface between the lattices and the skin is a weak point. It's a failure point. You have stress concentrations, you have sharp angles, and oftentimes that's where your part's going to fail first. Now, the way to remedy this is we actually want to drive a blend, or as you may call it, a fillet in other software, to give it sort of a rounded geometry so you can alleviate some of that stress concentration. Now, if you've worked in other softwares, usually the way we do this is when we have a certain infill geometry, we've got to go in and we've got to select edges that we want to fillet in the software. Not only is this a tedious process, you can see how it quickly becomes difficult to even have line of sight to actually select those edges. But, you know, if we have a simple geometry, we might be able to do it, maybe a few hundred, take the time, get it done. But then if you change that geometry, you're gonna have to go back and do that. It's likely you're gonna have rebuild errors. So what we do instead in Platform is we let the fields of the lattice and the skin drive that blend. So here we have this variable, blend radius. I'm gonna make that 3 millimeters. Let's have it rebuild and just give it a second. And what it's gonna do is it's gonna add that fillet at the interface between these two implicit models. So now you can see we have this nice blend along the edges. Really helps us alleviate that failure mode, that delamination error that we might see. So now we have a final part here. And what I want to do is take some time to show you how we can do this, but we can also use fields to drive other parts of the geometry. So what I'm going to do is I'm going to use a plane to drive the thickness of the lattice. So maybe I don't want the lattice to be uniform thickness throughout the part. So what I'm going to do is I'm going to bring up this field viewer here. And the field viewer is going to actually let us go in and inspect the fields that exist within Platform, which is very unique to Platform. So now what I have is I have a plane kind of defined by this line here going up and down. And that plane basically comes straight out of the screen. So you can see going from sort of white to black, that's our positive space, blue to pink, that's our negative space. These white lines here are basically 10 millimeter intervals. So this is 10, 20, 30, and so on. And in the negative direction, negative 10, 20, 30. So what I've done is I've defined this ramp that basically says I have a maximum beam thickness of 3 millimeters and a minimum beam thickness of 1 millimeter. So where that plane was, starting from that plane, the thickness is going to be 3 millimeters. And as we move away from that plane, we're going to gradually decrease to 1 millimeter. So I have this rib modifier here that had my original beam thickness. I'm going to remove that. I'm going to move in this plane ramp modifier. So again, all of this is rebuilding real time. So we're going to drive this geometry with this plane. And now you'll see there's the plane. The plane was there. As I described, we have the 3 millimeter thickness here. And then in the far regions, we go all the way down to 1 millimeter. So now we have a part. And what we want to do is we want to get it ready for manufacturing. And we want to, first thing that I want to do is what I like to do is kind of first translate this part. So this part was imported in a certain geometric space. So this translation step basically moves it to the 0 build plane. So I like to think of it as putting it on my build tray for whatever additive manufacturing process I may have chosen. So I've just moved it up in space. I also might want to rotate it. So I'm going to give it this negative 60-degree rotation. Maybe I just want to orient it for optimization for my build. So I can maybe minimize residual stresses. I can minimize the amount of support material that I need to use. So now this is rotated. So this is the orientation that I've decided, or maybe my manufacturing team has decided for me. And you'll notice that this lattice is pretty complex. And as your part gets larger, that complexity increases. Bringing this out into an STL file or any other type of mesh can be pretty tricky. And that file size can get pretty huge, cumbersome to move around. So what we propose is actually creating our own slices within nTopology platform and actually sending those slices, those contours, those hatches directly to our selected AM process, whatever machine you've chosen. So we've got this final part on the build tray. We're going to have this slice stack generate. We've decided that we want a feature tolerance of 0.1 millimeters. That means that any feature equal to or greater than this size will be resolved in the contours. I've chosen a spacing of 3 millimeters. Normally you would choose this based on your selected additive manufacturing process. The start height is 0, so we want to slice starting from the bottom, and we want to slice the whole part. So I've left maximum height empty. So we can go in here and we can see this slice stack. Now we have these contours here. Again, they're spaced 3 millimeters apart, as I mentioned. But not only do we have the contours, we also have the hatches in between. So I've defined a hatch spacing of 1 millimeter. So we have these hatch lines here in white. They're spaced 1 millimeter. Every time we increment a layer, we also have a 45-degree offset to help deal with residual stresses. So you can see the hatches going this direction here. In the next layer, they've been rotated 45 degrees. And you can change that on a part basis. You can even change that in different regions of the part. What we're trying to do is really give you full control over how you choose to export your part. So now we have sort of a manufacturing ready part. But what I want to show is nTopology's ability to capture different workflows from different teams. So we have these slices. Now, what happens if we want to change the original design? So what I want to show is a stress analysis result. So just a very simple simulation. Maybe this is a result from my simulation team coming in late stage. So we have some very simple constraints around the mounting hole. Not sure if you can see those there, but that's them in red. And then we've also applied a load on the pedal. And what we're seeing here is a map of the von Mises stresses of the part based on that constraint and that load. So we have this result. And what we want to do here is now we're going to take this result, this stress analysis result, And instead, we're going to drive the lattice thickness with this stress ramp. So we've gone all the way back to sort of our definition of lattice thickness, and we're driving that again instead of with the plane, with real world simulation data. And this is going to take a minute to regenerate if you're a little bit patient with me. But not only is it going to regenerate the part geometry, it's going to regenerate the orientation, the translation to the build tray, as well as our slice stack. So I'm going to bring up the slice stack just to show you what that might look like, but I'm also going to show you the part. So it's going to take a second to render, but trust me, it's here. All right, so now we've got that full part. And if you remember, if you look at those stresses, you've got high stress regions here, and that's been mapped to the lattice thickness on the final part. And just by adding that modifier in the original design, we still get an output of our slices, our hatches, our contours that we can take directly to our selected additive manufacturing process. So what we're really doing here is we're enabling all of the different parts of your cross-functional multidisciplinary engineering teams to work on the same part at different times in series, in parallel, and make design changes while understanding that a single design change isn't going to require lots of work from their other team members in these other divisions and departments. I mean, what this does is it gives you, it empowers your engineers the ability to make these changes to really drive the innovative nature of your parts and the performance of them. So this concludes my demonstration here in nTopology platform. I'm going to jump back over to our slides here. So just to recap about the things that I went through, we have intelligent data management, streamlined engineering design process, and as I showed, those design changes rebuild all the way downstream, so you can complete a workflow, you can go all the way back to the beginning, make some simple changes, and have that rebuild all the way down to manufacturing ready outputs. This helps reduce product development time, but it also enables your team to just work quickly, iterate quickly, and create truly innovative components. So I'm going to hand this back over to John at this point, and he'll wrap us up.
Blake, thank you very much. That was very informative, very fun to watch. A couple things to talk about, some calls to action before we go into questions and answers. If you would like a personalized demonstration of this software, of what Blake showed you, if the wheels are ticking and you wonder how this could be integrated into some of your workflows, if you have questions, please just reach out to us, sales@nTopology.com. Also, if you are watching and you are part of a 3D printer OEM, if you're a manufacturer and you are interested in the least in partnering with us, we would love to hear from you. I think Blake or Alex mentioned that part of our output is going right to contour slice data that's sent directly to 3D printers, and we would like to talk with you about further partnership and how we can integrate. Also, we have been ramping up our blog series quite a bit more lately. Visit nTopology.com/blog. We're trying to put out more and more of those very informational readings every week to educate you on topics like implicit modeling. We've got several more of those in the pipeline to come. And for future informational sessions like this, head to nTopology.com and you should see those on our banner. So we'd like to turn it over now to some questions, and we're going to try our best to answer all of those.
All right, well, thank you to all of our presenters today. Looks like we've got a couple of questions coming in. So start with the first one here. Does this work only with metal 3D printing?
I'll take that question. So no, we actually have designed platform to accommodate different types of additive manufacturing processes, and we're currently in the process of continuing to build out integrations with different technologies. So whether it's metal, polymer, potentially ceramic, I think we can handle it all.
All right. So next question. So did the FE results just guide the lattice sizing gradation, meaning a new analysis was not done within nTop with the new lattice design?
That's correct. So in this workflow, all we're showing is the ability to drive geometry with the analysis. And really what we're trying to do with our analysis capability, our simulation capability within platform, is give you quick tools to not only do simple analysis for early stage, but also design space exploration. The idea is that once you have a final model that you're satisfied with, you're going to send it over to have the part fully analyzed with your traditional tools. We're not trying to replace validation. We're just trying to be an early stage design exploration tool to help you do that.
All right. Is this cloud-based or local, and what type of specs are recommended?
This is Alex here. So this is all locally based. And I would say, as far as computer specs, we were running this demo off of a laptop. So any modern, design like CAD workstation will work extremely well for this software. I'd say a good GPU and at least 16 gigabytes of RAM is a good baseline for requirements.
All right. Next one. How does this solution work with my existing design solution?
What I showed earlier in the demonstration was the ability to import boundary representations from other CAD software. So what I wanted to show is that platform does play nice with other tools that you might be using. What we see is that typically people use this workflow from the beginning. However, once they kind of see the benefits and the real power of implicit modeling, they start to shift designs towards implicit first. That way, it's just a little bit easier to drive things with fields. You have all of the field information, and you don't have to worry about importing new geometry from a boundary representation. But it's definitely possible.
All right. Is the main application for your software lattices?
And John touched on this a little earlier in his presentation. One of our first products was Element, and that was certainly a lattice generation and editing tool. We learned a lot from creating that piece of software, and what we realized was that not only was Implicit great for representing lattice structures, it was great as an engineering tool. So Platform is much more beyond just lattice generation and editing. It's a full-blown modeling software.
All right. Let's see. Is it possible to generate support structures for the body?
Currently, we don't have support structure generation as a one-click option. However, you do have the freedom to generate those structures yourself in Platform. I will say one of the things that Platform does very well is basically Boolean and offset operations. These things just don't really fail, and you'll see that often happens in boundary representation modelers. So we have explored generating our own support structures, and it's certainly in the horizon for product development to be able to do that as a function within Platform using the block system.
All right. Does a beam have a uniform radius, or can it be a variable?
Absolutely, it can be a variable. So I did show driving that beam thickness with the plane. There are many ways in which you can do that. You could drive it from really any implicit geometry. So if you can remember back to the field viewer that I showed with that plane, that's the field of the plane implicit. But every implicit has a field, and you can use that to drive your thickness, or you can just set it as multiple variables. It's really up to you in your design process.
All right. So another exporting question. Will PNG slice exporting be supported for DLP-based systems?
Yeah, this is Alex here. That is coming shortly. It's been a big request, and it's on a roadmap.
All right. Can you create specific internal structures? Are these presets, or can you model them yourself?
Currently, platform ships with a set of unit cells. However, it is possible to create your own unit cell, whether that's beam-based, face-based, really anything within a unit cell that you'd want to put inside.
Okay. Does it use single thread or multi-thread?
Platform is fully multi-threaded. So the more cores you throw at it, the faster it's going to be. It's really great. We do keep one core open for the GUI. So if you are running really intensive processes, it'll take up every core except for one, but you have one to change variables, create new blocks, edit blocks, and make changes while all of that's happening in the background.
If a BREP geometry or STL is imported, is it converted into an implicit mode?
So you bring it in as a mesh or an STL, and then that's usually the first operation that you would do is convert it to an implicit model, and that is a one-click solution.
All right. Can you run FEA on any lattice structure?
So FEA, as you probably know, gets a bit difficult when it comes to lattice structures because they're complex. We have certain work in the pipeline to develop strategies to do analysis on lattice structures. But again, it really depends on the complexity of your model, as I'm sure you're aware.
All right. Do you have specific OEM printer drivers that are needed to print the part files, or how are parts sent to the printer?
So for that, we are exporting slice files. So these are slice files specific to the OEM. So right now we have slice file export as the CLI, which is kind of the common slice file format, and that could be used for concept laser. EOS is coming, and also Arcam and Renishaw are in the works too. We're working closely with OEMs to make sure that it could get into your build processor, so kind of direct to machine.
All right, so it looks like we have time for one more question. Would it be possible to show some of the re-entrant unit cells?
Kind of showing that here, hopefully it was a fairly self-explanatory. I've taken the model that we were working with earlier, and I've just shown this re-entrant unit cell on that model. It's a bit of a messy cell, but there it is. And yeah, there's for people who are interested, just leave this kind of up there. There's the list of unit cells that ship with platform, and then again, the ability to create your own.
All right, so with that, we'll wrap up today's presentation. I do want to let you know that if you asked a question, all of those have been recorded, and so if we didn't answer them in the Q&A, nTopology can follow up with you afterwards. Thank you to nTopology and all of our speakers today for making this webinar possible, and I want to say thank you to everybody listening in as well. You'll receive an email with a link to the recording of this webinar within the next couple of days. Thank you for joining us. Enjoy the rest of your day.
Thank you.